Anyone who's been in the hobby for a while will know exactly what a perfect pass is. Launch control for your RC speedrun car. It's essential for those high-speed runs. But have you ever wondered how it works, and can you make one at home yourself? Let's find out. Oh, that's not right. Before we get into it, we're going to have to learn a little bit more about how the transmitter and receiver work. What does that signal look like? And how do we manipulate that signal in order to get the car to do what we want it to do? Let's see if we can figure it out. Every time you pull the trigger on your RC car, something pretty clever is happening behind the scenes. There's a whole signal chain from your finger through the air all the way to the motor, and at the heart of it is a signal called PWM. Let's break it down. PWM stands for pulse width modulation. Sounds fancy, but it's actually pretty simple. Think of it like a light switch. If you flip it on and off really fast, like faster than you can see, the light looks dimmer. The longer you keep it on compared to off, the brighter it appears. That's basically what PWM does. Instead of sending a voltage that smoothly goes up and down, it sends a signal that's either fully on or fully off. The trick is how long each pulse lasts. That's the width in pulse width modulation. So in the RC world, there's a standard. The signal repeats every 20 milliseconds. That's 50 times a second. But the important part is the length of each pulse. 1.5 milliseconds means neutral, the motor is stopped. Crank it down to 1 millisecond and that's full reverse. Push it up to 2 milliseconds and you've got full forward. Everything in between is just somewhere in between. 1.2 milliseconds is a gentle reverse. 1.8, solid forward. It's all just a number on a spectrum. In practice, you'll see microseconds, not milliseconds. Same numbers times 1,000. 1,500 microseconds is neutral, 1,000 is reverse, and 2,000 is forward. So the receiver's job is pretty straightforward. It gets this repeating pulse, and all it has to do is measure how long each pulse stays high. Basically, it's just running a tiny stopwatch. Signal goes high, start the clock. Signal goes low, stop the clock. And that measurement tells it exactly the position the trigger is in. If the stopwatch reads 1.5 milliseconds, the trigger's in the middle. Less than that, you're pushing it forward. More than that, you're pulling it back. It then passes that information along to the ESC, which decides how much power to send to the motor. Let's see the whole thing in action. You pull the trigger, the transmitter generates a PWM pulse. Let's say 1.8 milliseconds for a nice forward push. That pulse is sent over to the receiver. The receiver measures it, 1.8, that's a good amount of forward. It tells the ESC to send power to the motor. And just like that, you're moving. The whole thing happens 50 times a second. Every 20 milliseconds, a fresh pulse, a fresh measurement. It's this constant conversation between your finger and the car. And that's PWM in a nutshell. One simple signal, 3 key numbers. 1, 1.5, and 2 milliseconds. And a constant conversation between your hand and the motor. Pretty elegant for something invented decades ago. So here's the problem. When you pull the trigger all the way, the receiver sends 2,000 microseconds straight to the ESC. That means full power. If you've got a powerful motor, the tires are going to spin. But what if we put something in between? A microcontroller or throttle manager that sits between the receiver and the ESC. It receives the full 2,000 microsecond from the receiver, but instead of passing it straight through, it starts at say 1510, 1520, 1530, and so on. The motor gets a little more power each time, smooth, controlled progression. And eventually, it reaches full power, but by then, you're already moving. Now we understand how the transmitter gets that signal to the receiver. what the signal looks like when the receiver receives the signal and how it sends it to the ESC. And we've worked out that if we put something in between those two to manipulate that signal, or effectively just slow it down, then we know what to do. But now we need to build it. So we're going to have to buy some components. The heart of the build is an Arduino Nano. It's cheap, it's small, and it's got everything we need. A processor to run our code, and enough pins to read the receiver signal and output to the ESC. We'll stick it all on a breadboard for now. It lets us prototype things without soldering anything. If we mess up, we just pull the wires out and start again. We're going to need a couple of resistors on the signal lines, one between the receiver and the Arduino, and one between the Arduino and the ESC. They're just there to protect the Arduino's pins. And then we'll need a potentiometer, which is basically just a dial, and that's going to allow us to adjust the ramp size on the fly. Turn it one way, increase the delay, the other way, reduce the delay. We'll need an ESC and motor to test with, and a spare transmitter and receiver. And then, of course, we'll have to write some software to run the whole thing. This is not an original Arduino board at all. It's just an Amazon special. I think they were a couple of pounds or something. And this board is just for those that don't know what an Arduino is, it's basically just a controller board. It comes with a microprocessor, cheap AT microprocessor, comes with a switch on it, and it comes with USB-C. That's pretty much it. So it comes with these headers. So we're going to need to solder these headers on, and I'll just quickly do that now. And so with that done, we have these legs to be able to push this into a development board. And what we'll use for that is just this development board here. And what we can do is we can just push this down into the board like so. And that just means that we can use these pins, these sockets for pins, to be able to wire things to the board in an easier way. So with that done, on to the next step. And with the Arduino headers soldered to the board, the only other soldering we need to do is just to create some wires and pin attachments for a potentiometer. So I'm just going to quickly solder these now, and then we'll start getting everything wired onto the board. Now that we've got everything soldered, we've got the Arduino Nano with the header pins soldered to the board, pushed into the development board. We've got the potentiometer with some leads on it. We've got a servo lead that I've just cut the end off and just crimped these pins so I can push it into the board. And I've put a small header into the servo connection for the ESC. Aside from that, I've got a couple of small resistors, just the smallest I had in the cupboard, to be honest with you, just to stabilize the signal for the ESC and the receiver. Aside from that, everything else is fairly straightforward, so I'll just whiz through getting this wired up, and then we can talk about what goes where once we've done that. And there we have it. I think that's pretty much there. So what we've got here is we've got the ESC plugging onto an empty space on the board. It gets a ground and a plus 5 volts from this positive and negative rail on the board. The positive and negative rail on the board are fed from the plus 5 volts and the ground, which comes from the Arduino Nano. That gets its 5 volts from the USB-C port when that's plugged in. Now, if you were to assemble this in a way that you would put it into a car, you wouldn't necessarily want the USB to serve the power because you wouldn't have necessarily a USB plugged into it. So therefore, you would want to do it sort of the other way around, and you would want to take the plus 5 volts out of the ESC and then power the board from that. So it would be slightly different. This is just a bench example. Then we've got the potentiometer here, which we're going to use to dial in how much or how little we want the delay to be. Again, plus 5 volts and ground from the ground and plus 5 volts rail here. And then the wiper, which is the signal of the potentiometer, going into pin A0 on the Arduino Nano. And then we've got the ESC, which connects to D9 pin on the Arduino Nano, and then the receiver coming in to D2. And as I mentioned earlier, we've got a resistor between the Arduino Nano and the ESC, and between the Arduino Nano and the receiver, just to stabilize that signal. So the port numbers or the pin numbers of the Arduino Nano will make more sense when we get to writing some software to upload onto the Arduino Nano. But for now, I think that's everything that we need for the assembly of the development board. Now that we've got the hardware sorted, we're going to need some software to run on the Arduino. So let's get onto the computer and see if we can write some code. Okay, I'll speed through some of this, but just to get us started, I'm just going to pull in the relevant libraries here and set up the pins that we're going to use on the Arduino for the receiver, the ESC, and the potentiometer. And then once we've got those, we'll add a pulse minimum of 1000, so that's the start of our range. Pulse maximum of 2000. We'll add a dead zone of 50, which we can go into in more depth later, but basically just means that we're active from 1950. And then we can add an invalid low zone, because we know everything below 1000 is invalid. We can add an invalid high zone, because we know everything above 2100 would also be invalid. Then we'll add our ramp ranges. We'll add the ramp minimum as 1 and the ramp maximum as 20. And that just means that every iteration of the loop, the minimum that we can increase the ramp is by 1 microsecond, and the maximum would be by 20 microseconds. And with that done, we'll create some functions, we'll whiz through this, and see you when we're done. push to the Arduino Nano. I've just connected a small battery that just happens to have the right connector, just a little 2S battery. And let's give it a try. What's the chances that it works first time? So we better get USB-C for the Arduino. Just plug that in there. Okay. So the Arduino's got power, we've got light, the receiver has power, the fan for the ESC has power. Let's turn it on. Turn on the transmitter. Nothing. Interesting. Ah, I see. Okay, let's try this. So let the Arduino boot, turn on the ESC. Okay, well that's not gone well. That's not what we are expecting at all. Okay, so what I did there was I removed the power from the +5 volt rail to the ESC, because we actually want the ESC to get power from its own BEC via the battery rather than via the USB port. So that's fine, but this feels software based, so I think functionally everything is working, but we won't give up. We'll keep trying. So as you can see, full power on the throttle means nothing on the motor. Neutral on the throttle means the motor's spinning. And then reverse or brake is doing nothing at all. Okay. Well, I think this could be a couple of things. It could be a number of things. It could be that the timings we're getting from the receiver don't match what we're anticipating, the standards that we talked about earlier. It could just be bad code. Let's get on the computer and have a look. So here we are back on the computer, and we'll just get rid of all of this code for now. We're going to push something nice and simple just so that we can read what we're getting from the receiver. So I'll just quickly run through this. Okay, let's take a look at what we've got. So we've just defined the pin for the receiver, created the setup function for the serial input, and then just running a simple loop which just detects what pulse is coming in from, or what pulse it's reading from the receiver. We'll compile that, push it to the Arduino, and then see what we get. And isn't this interesting? So we can see here, we're getting around 1240 microseconds on idle, which is not what we're expecting. And then we're getting the 1500 that we are expecting on full throttle. and then full brake is 990. So that's just not right, and that explains exactly why we're seeing what we're seeing. Interesting. Just as I finished that debug session, I had a thought about the transmitter and wondered whether or not the trim was the issue. And lo and behold, when I checked, the trim was moved all over the place. So I've corrected that now. Let's see if we get better results on the computer. And there we go. We're getting the right numbers. 1470, 1970, 996. Looking good. So here I'm just going to tweak the software a little bit. I'm just going to put in a launching flag, which means that we can track whether or not we're currently in an active launch mode, which just enables us to keep track of where we are. And then if we hit failsafe mode because we lose signal, we can snap right out of launch mode and return back to idle straight away. I'll speed things up a little bit while I get this implemented. I'm not seeing what I want to see here when I increase and reduce the potentiometer. We can see on the right hand side there that the potentiometer reading is going up and down, but I'm not seeing what I want to see on the output. I won't get into too much of the detail, but I think the issue is here with this line. I think it's the way the floats that are interpolated with C++. I think we're truncating 0.48 to 0. So I'll put a fix in for this and we'll see if it works. Okay guys, it's time to give it a test. I've pushed the latest code to the Arduino. Let's restart the Arduino and just see, wait for the Arduino to come up. Just look at where the potentiometer is. Let's wind the potentiometer back to 0, which is there. Turn on the ESC. So with the potentiometer at 0, we should see it pass straight through. So 2000 microseconds from the controller to the receiver, 2000 microseconds straight through to the ESC, so we should get full power, which we do. Okay, now the moment of truth. Let's wind the potentiometer all the way back. We're at 1023, so that's maxed the other way. That should be the maximum ramp. Nice. One more time. I don't know if you can hear that. Just move it closer to the microphone just in case. It works. And then we back off the potentiometer again, straight through. And then let's get the potentiometer about halfway. I was a little over halfway there. It's probably about halfway there. Yeah, and it ramps up a little quicker. Well, there we go. It works. At the beginning of this video, the question was, can we learn how a perfect pass works? And can we make our own at home? Well, yes. Yes, we can. But here's the thing. Should we? Probably not. The perfect pass is professionally made, it's battle tested, it's reliable. Raz and his team have poured a lot of time and effort into perfecting the design. And honestly, it's inexpensive for what it does. Do I think that we could condense everything that we've made into something small enough to put into a car and actually run with? Yeah, I think we could. But why bother? I did all of this, and I'm still going to buy one. Just buy a perfect pass.